Good morning everyone. So, we are discussing about the filtration of charged colloid particles in presence of external electric field. Now, these charged colloid particles have typical characteristic because they are charged. Now, under an action of external electric field, an electrokinetic phenomena will initiate, and that is known as electrophoresis. In fact, under the presence of external electric field, there are several electrokinetic phenomena that will occur at a time in a solution that we have discussed in the last class, and they fall under the category of electrophoresis, electroosmosis, sedimentation potential, so on and so forth. Now, in this case, it is very important to understand how an external electric field will facilitate the transport of a charged particles in an aqueous solution. That will enhance the performance of the filtration, and that will enhance the performance of the enhance the productivity of the whole filtration process. But before going into quantification of the enhancement that will occur due to the presence of external electric field for the filtration of the charged solutes, we we need to know some of the fundamentals of electrokinetic phenomena, and later we will just look into how the behavior will occur of the electrolytic solution in presence of a charged surface. So, we have already seen and we will reiterate again in this class that when you place a charged solute in an electrolytic solutions, there will be a new distribution of the charges that will occur inside the solution, and that distribution will be the counter ions will be very close to the charged surface, and the concentration of the coions will be very small. So, there will be increase in counter ion concentration close to the surface, so that will give rise to the concept of zeta potential. And if you remember what is zeta potential, it is basically an envelope of a solid particles that move under an external electric field in an electrolytic solution where the viscosity will be infinite. That means, it moves an envelope, it moves in an electrolytic solution under the presence of external electric field, okay, and that envelope will be always attaching to it, okay, and that envelope will be mainly constituted by the counter ions. So, the actual potential of the charged particles will never be measured. One can measure the potential of the charged particles on the outer surface of the envelope, and that potential is known as the zeta potential, and that can be measured by a zeta sizer or zeta meter. So, what zeta meter will do, zeta meter exactly will measure the potential on the outer surface of the charged particle, not on the actual particle outer surface. Okay. So, in order to quantify all these phenomena, we have to find out how the concentration profile will look like when you place a charged surface in an electrolytic solution. Okay. So, let us look into the concentration profile of ions in electrolytic solution in presence of a charged surface. Okay. Suppose we place a positively charged surface in an electrolytic solution. As we have discussed that if you place a positively charged surface in an electrolytic solution, the counter ions will be accumulating over near the surface, and the coions will not. Okay. So, there will be build up of concentration of the counter ions close to the surface, and that will keep on decreasing and going into the bulk. Similarly, on the other hand, the coion concentration will be pretty less, will be very less, and it will be depleted near the surface, and it will gradually increase, and at the bulk the electroneutrality will be maintained. So, this is the concentration profiles of counter ion. And this is the concentration profile of coion. And here you will be having the bulk of the solution, and the bulk of the solution, in the bulk always electroneutrality will be maintained. Okay. and this is the distance away from the charge surface, and at x tends to infinity, that means the bulk of the solution electroneutrality condition should be maintained always. Okay. So, Z plus N0 plus Z minus N0 minus will be always equal to 0, or is Z plus is the valency of the positively charged ion, Z minus is the valency of the negatively charged ion, and N0 plus is the concentration of positively charged ions, and this is expressed in number concentration. That means, number of such ions per unit volume of solution. So, number per meter cube. So, if you know the molar concentration, you change the molar concentration into, molar means gram per liter, you change into gram per meter cube, multiply by 1000. Okay. So, gram per, and then you divide by molecular weight, it will be gram mole per meter cube, and then multiplied by the Avogadro number, that will give you the number concentration, numbers per meter cube. So, that is how one can have a unit change from molar concentration into the number concentration. Okay. So, Z plus is valency of cations, positively charged ion, Z minus is valency of negatively charged ions, N0 plus is the number concentration of cations, cations means positively charged ions, and N0 minus is number concentration of anions or negatively charged ions. So, and all these are expressed number per meter cube. Okay. So, you can write down this expression if you would like to. So, it will becomes Z plus N0 plus minus Z minus N0 minus is equal to 0. Okay. Now, we define, so that is the form of electroneutrality condition at the bulk. The potential, now we define the potential energy of an ion in an electric field at a distance x from the surface. This potential energy is defined as phi of x is equal to Z E psi at x. So, this is the potential energy, this is the potential energy, and this is the potential at that particular point. It should be multiplied by the E, the electronic charge, and Z will be the valency. So, if you remember, the energy, potential energy will be nothing but the charge multiplied by the potential at that particular point. So, if you remember the laws of electrostatics. Now, at the steady state, we say net ion flux will be is equal to 0, and net ion flux we denote it by J, okay, and flux is number per meter square per unit time. So, that is the net ion flux, and these ion flux will be constituted by two components. So, there are two components of this flux. One is the diffusive flux, okay. What is the diffusive flux? Diffusive flux is basically that will arise because of the concentration gradient of the ions between two locations. Okay. So, the ions will move from location 1 to location 2 because of the presence of concentration gradient, and that will be occurring because of the presence of diffusive flux. So, this is due to concentration gradient Secondly, flux due to electric potential gradient. Okay. Since there is a electric potential present, and this potential will be different between the two locations, that gradient will drive the ions from location 1 to location 2. So, because of the presence of these two fluxes, the net flux will be equal to 0. So, if you write down the net flux equation at the steady state, it will be minus d dn dx plus n by f d phi dx. Okay. So, this is the concentration gradient Fick's law, and this is the potential gradient and F is the friction factor. Now, this friction factor F will depend on the geometry of the solute and the size of the solute, so on and so forth. So, if at the steady state J should be equal to 0, and you will be having minus dn by n is equal to d phi divided by f d, and f is given as k b t divided by d, and this is known as Stokes-Einstein equation. Okay. And where is Kb? Kb is Boltzmann constant. T is temperature in Kelvin. D is solute diffusivity. Okay. So, one can integrate this equation out. So, if you can integrate that equation out, what you will be getting is something like this: dn by n is equal to 1 by kbt d phi from 0 to phi at any x location, and this from n0 to n at any x location. Now, the implication of the boundary condition is very important. At any x location, the potential energy is phi, and the constant number concentration is n at any x location. On the other hand, the potential energy will be 0 at the bulk of the solution. Okay. That means bulk phase do not realize or experience the presence of a charged surface in the electrolytic solution. So, the potential energy of the bulk phase will be equal to 0, and what is the concentration of the solute there? It will be the bulk concentration. Suppose you are using 0.01 molar NaCl solution. So, the number concentration will be corresponding to the 0.01 molar. Okay. Then you have to convert the molar concentration into number concentration the way we have discussed earlier. Okay. So, if you do this, then you will be getting a distribution of number concentration of the ions in the electrolytic solution as n0 exponential minus phi x divided by kbt. Okay. Now, this distribution is known as Boltzmann distribution. That means the concentration of the coions, concentration of counterions will decrease exponentially from the surface. The concentration of the coions will increase from the surface exponentially up to the bulk. Okay. next we define the charge density. This is given as rho. Now, concentration, let us write down the concentration of ith type of ion is given by the Boltzmann distribution. Ni is equal to Ni naught exponential minus phi divided by kBt. And what is phi? It is nothing but Ze psi. And what is psi? Psi is the potential at the location x. So, Ni is given as Ni naught exponential minus Zi e psi over kBt. Okay. So, if we are talking about the chloride ion concentration, then Zi will be minus. If you are talking about the sodium, then Zi will be plus 1. Okay. So, and psi is the potential at any location x. So, for positively charged surface, suppose you insert a positively charged surface in an electrolytic solution, the number concentration of counter ions will be Ni naught exponential Zi e psi over kBt, right, because Zi will be positive, negative there. So, negative it will be positive, and number concentration of counter ions will be Ni naught exponential minus Zi e psi over kBt. Now, actually, if you know the distribution of the potential at any, as a function of the location x, the x is from the distance from the charged surface, you will be able to know what is the exactly concentration profile as a function of location. So, our next aim is to find out how psi varies with x, but before that we have to find out what is the definition of charge density, because that will be, you will be requiring that definition time and again. Now, let us consider a symmetric electrolyte. Symmetric electrolyte, let us say it is called Z is to Z, that means NaCl, okay, both the valencies are equal. Okay. So, that means Z plus mod of Z minus will be equal to Z. Okay. So, it is sodium chloride. For example, if it is a calcium chloride, it is 2:1 electrolyte. If it is a aluminum chloride, it is 3:1 electrolyte, and these are called asymmetric electrolyte. Okay. So, concentration profiles of, so for a Z is to Z electrolyte, you have the concentration profile of counter ions and co-ions. N plus is n plus 0 exponential minus Z e psi over kBt, and n minus is n minus 0 exponential plus Z e psi over kBt. Okay. And net charge density is defined as rho. So, it is number of charges per unit volume of the solution. It is defined as rho is nothing but summation of Zi e Ni. Okay. I is equal to 1 to 2 or whatever, 1 to 3 or whatever. Okay. So, basically if you have the, it is summation of all the number concentration multiplied by the Coulombic charge 1.6 into 10 to the minus 19 Coulomb multiplied by the the valency of the corresponding ion. The whole thing over a summation will give you the charge density, that will give you the number of charges per unit volume. So, for symmetric electrolyte, rho is summation of Zi E Ni naught exponential minus Zi E psi over kBt, where this psi will be a function of distance, okay, at every location. So and this we know this Ni is nothing but given, it will be given by the Boltzmann distribution. This is nothing but the Boltzmann distribution. Okay. Now, let us look into the potential distribution. How psi is varying as a function of x. Why this potential distribution is important? You require to find, unless and until you know what is the variation of psi as a function of x, you will be unable to find out how the concentration, number concentration varies as a function of x, how the charge density varies as a function of x in the solution. So, it is important to to estimate the potential distribution, and for the first case we consider a flat plate model. What is this flat plate model? We assume that a charged flat plate is immersed in an electrolytic solution with its surface potential psi naught. Okay. Assume a charged flat plate with surface potential psi naught is immersed in an electrolytic solution. Okay. And the potential distribution that you know it is given by the Poisson's relationship, right. Is given by the Poisson's equation. Okay. So, let us look into the Poisson's equation and how it takes the form in one dimensional case. Is given by rho is nothing but divergence of minus epsilon of gradient of psi. Okay. This is the generalized form of Poisson's equation. Now, what is rho? Rho is the charge density, and we have already defined the charge density earlier. And what is psi? Psi is the potential at any location x, let us say. And what is epsilon? Epsilon is dielectric constant of the medium. And what is dielectric constant? Dielectric constant is given as epsilon 0 times d. This is the epsilon 0 is permittivity in vacuum, and d is the dielectric constant of the medium. I think these known as permittivity, right. Epsilon is permittivity. So, it has two components, dielectric constant of the medium multiplied by the permittivity in vacuum. Okay. So, dielectric constant of medium, and for water what is the value of dielectric constant? It is 80, that is correct, and permittivity of vacuum is 1 by 9 into 10 to the power 9, something like that. Okay. So, we will look into that. So, for constant value of dielectric constant, with the form of Poisson's equation, this equation takes this form, grad square psi is minus rho by epsilon. Okay. So, this is the form of dielectric of the Poisson's equation, the potential distribution for constant dielectric constant, and under one dimensional Cartesian coordinate, this will be nothing but d square psi dx square will be is equal to minus rho over epsilon, right. And since we have already defined the definition of expression of charge density, and charge density will be in terms of number concentration of the ions, which is known as a Boltzmann distribution. Just insert there in this equation and see what you get. So, you will be getting d square psi dx square will be minus 1 over epsilon summation z I n I naught. I think there will be an E here, z E psi n I naught exponential minus z I E psi over k b t. Okay. This equation is known as the, and this summation is over 1 to 2 if there are 2 ionic species are present. For example, NaCl, there will be 2 terms only in this summation. In one case Zi will be plus 1, in another case Zi will be minus 1. Okay. Now, this is a Poisson's equation, and here you have inserted the Boltzmann equation. So, this equation is known as Poisson-Boltzmann equation. Now, there is a simplification of this whole problem if we neglect, if we expand the exponential term. That exponential term can be expanded if the quantity z e psi over k b t will be much less than 1. So, for z I e psi over k b t much less than 1, there is a simplification, there is a mathematical simplification of this Poisson-Boltzmann equation, and this assumption is known as Debye-Hückel approximation. Okay. And typically this approximation is valid if you have a surface potential around 25 millivolts or less. Valid for surface potential is less than 25 millivolt. That means, it has a fairly good applicability even if you have a surface potential around 40 millivolts, still you can use the Debye-Hückel approximation. Now, under this approximation, and if you open up this summation series, if you open up the exponential term, you will be getting 1 minus z e psi exponential e to the minus z e psi by k b t will be approximated as 1 minus z e psi by k b t, and you neglect the higher order terms. Okay. So, you will be getting d square psi dx square is equal to minus 1 by epsilon summation z I e n I naught minus summation z I square e square n I naught psi over k b t. Okay. Now, if you remember the first, there are two terms of the on the right hand side now. The first term will correspond to the electroneutrality condition. If you remember, the bulk of the solution always the electroneutrality will be maintained. So, summation of Zi E Ni naught will be equal to 0, because to satisfy the electroneutrality condition. So, this term will vanish because of electroneutrality condition. And then this term will be 1 minus 1 by epsilon will be multiplied by the second term, and this minus minus it will be plus, and the whole equation now becomes the Poisson-Boltzmann equation now becomes d square psi dx square is equal to 1 by epsilon k b t summation of z I square E square n I naught psi. Okay. Now, if you remember, this psi is same for both the terms in the, if you open up the summation that only terms that will differ whether it will be plus 1 or it will be minus 1 the z. Okay. And now these can be written as kappa square psi. You can write kappa square is equal to under root square summation z I square n I naught divided by epsilon kbt. Okay. Now, if you do a dimensional analysis of this kappa will be under root of this. Okay. And these will be having a unit of length inverse, that means it will be having a unit of meter inverse. Okay. So, kappa inverse will be having a unit of length. This particular length is known as the Debye length. So, on which factors the Debye length will depend? Debye length will depend what is the it is entirely a characteristic of electrolytic solution, electrolyte concentration, nature of the electrolyte and the solution environment. So, this will be a function of concentration of electrolyte, how the concentration of electrolyte will be appearing, that will be appearing in the number concentration Ni naught, and nature of the electrolyte, how the nature of the electrolyte will be basically reflected in the value of Zi. Okay. And solution environment, that means epsilon, and of course, the temperature. Okay. And what is the physical significance of this Debye length? This physical significance is that it gives an idea what is the region. Suppose you put a charged surface in an electrolytic solution, and there will be a concentration profile, okay, of the counter ions, and these will be the co-ions, and this becomes the bulk of the solution. So, this distribution of the charges, as we have discussed in the last class, this is known as the electric double layer or EDL. So, this thickness is nothing but EDL. Okay. And the thickness of the electric double layer will be dictated by the value of the Debye length. That means, if you have a very small Debye length, then we can call it say thin double layer, and if it is a high Debye length, we can call it say thick double layer, or it is known as the diffused double layer. So, double layer thickness will be dictated by the Debye length, and it gives an idea what will be the region of influence of the charged surface in the electrolytic solution. That means, beyond the value of the Debye length from the charged surface, the influence of the charged surface on the electrolyte solution will be negligibly small. Okay, that is the physical interpretation of Debye length. Now, what we can do? The governing equation of Poisson-Boltzmann equation is nothing but it is boils down to kappa square psi, and you can integrate this equation with the boundary condition at x tends to infinity, psi is equal to 0. That means, at the x tends to infinity means at the bulk of the solution there is no influence of the charged surface, that means potential will be exactly equal to 0. Okay. And at x is equal to 0, the surface potential is known to us, it is psi 0. Okay. Now, if you integrate it out, the solution that you get after integration is, it will give you the potential distribution as a function of x psi 0 exponential minus kappa x. Okay. So, this distribution is generally obtained. So, you should remember what are the underlying principles or assumptions that are required to have this distribution. This is of course obtained under the Debye-Hückel approximation. Under Debye-Hückel approximation, you can say the potential will be decreasing, will be declined exponentially from the surface towards the bulk. Now, of course, Debye-Hückel approximation is valid if your psi naught will be less than 25 millivolt. If your surface will be having a high zeta potential or a high surface potential beyond, let us say 50 millivolt or 60 millivolt or 80 millivolt, you cannot use this analysis. So, there is a shortcoming of this analysis. If you have a surface potential in the order of 25 millivolt, even it works better if you go up to a potential up to around say 40-50 millivolt. But beyond that, if you have a high surface potential, you cannot use this equation as a potential distribution, because the validity is not it is not valid under those situations. Okay. So, one has to get a more valid situation if we have a high surface potential. Okay. Now, let us look into a more generalized solution. More generalized solution of potential distribution for a Z is to Z electrolyte in flat plate geometry. Okay. So, we write down the Poisson-Boltzmann equation for Z is to Z electrolyte. The simplest version of Z is to Z electrolyte is NaCl. Okay. So, this becomes d square psi dx square minus 1 over epsilon summation Z I n I naught exponential minus Z I e psi over k b t. Now, you have to solve this equation. In order to solve this equation, you multiply both sides by 2 psi d psi dx, 2 d psi dx, right, and then integrate. You will be getting, if you do that, that means you multiply both sides by 2 d psi dx, d square psi dx square minus 1 by epsilon, this whole term 2 d psi dx, and then you integrate it out. The integration result will be d psi dx whole square will be given as, there is a left hand side and right hand side, it will be 2 by epsilon summation of n I naught Z I epsilon 0 to psi exponential Z I e psi with minus k b t d psi. Okay. So, this will be simplified to d psi dx whole square will be 2 k b t divided by epsilon summation of n I naught exponential minus z I e psi over k b t minus 1. Okay. So, for symmetric electrolyte, we have Z plus is equal to minus Z minus, right. So, basically mod of Z plus is equal to mod of Z minus will be is equal to, let us say we denote it by Z. It is like NaCl, right, plus 1 minus 1. So, mod value will be 1. So, modulus of Z plus and modulus of Z minus will be denoted by, let us say it is Z. So, d psi dx whole square becomes, if you now you open up the summation series for species ionic species 1 and ionic species 2, it will be 2 kBt N0. N0 is the bulk concentration, Ni naught will be basically N0 for both the ions, okay, divided by epsilon exponential Z e psi over kBt plus exponential minus Z e psi over kBt minus 2. Okay. And this expression can be simplified. I am just overlooking the one step, and it will be finally taken as d psi dx will be minus 2 kappa. Okay. Kappa is nothing but the inverse of Debye that we have discussed earlier, kBt over Z e sin hyperbolic Z e psi over 2 kBt. Okay. Now, you can integrate it, and this so when you take the square root of this equation, you take the negative value plus negative root of the right hand side, simply because psi will be decreasing as x is increasing, because x is the distance from the surface. Okay. So, one more integration, you do one more integration, and that will be giving you the distribution as a function of x, and this becomes tan h z psi bar by 4 is equal to tan h z psi 0 bar by 4 exponential minus kappa x. And what is psi bar? Psi bar is nothing but the non-dimensional psi, that is E psi over kBt. Okay. So, this is the generalized distribution of surface potential as a function of x for a Z is to Z electrolyte. And if you remember that this equation does not give an explicit expression of psi as a function of x, this gives a transcendental equation. Okay. So, if you would like to find out what is the value of psi at a particular x location, you have to solve it by trial and error, because it does not give you the explicit expression. Okay. So, the advantage of getting explicit expression is using the Debye-Hückel approximation if you have a surface charge less than 30 millivolts. So, this expression will boil down, it boils down to the earlier expression psi is equal to psi naught exponential minus kappa x if your psi 0 is less than 25 millivolt. Okay. So, in rare cases in our applications we will be utilizing this expression. In most of the cases we will be using the simplified version using the Debye-Hückel approximation, and also we have done this analysis. It is basically this is not relevant to our case. Our case is we will be having a charged protein solution or charged micelle solution, which will be moving along the electrolytic solution, and you are filtering it by using ultrafiltration or something. Why we have done this analysis? Because in order to find the solution environment, the charge environment, what is the value of surface potential around the charged sphere, it is easier to solve the rectangular coordinate. Okay. That is why, to give a demonstration of how the potential distribution will be occurring, even if you insert a charged surface flat plate in an electrolytic solution, we have done this analysis. Next, we will be doing the actual analysis, what is the charge distribution or the potential distribution around a sphere, because that will be of primary interest to us, because we are talking about the spherical colloidal charged colloidal particles, for example, the protein solutions, micellar solutions, like that. Okay. So, we look into next the double layer charge, double layer analysis. Around the charge sphere. Okay. This is very important that we are going to do. Now, why this is important, let me clarify it once again, because we are talking about the filtration of a protein particle or a colloidal particle which is charged by using ultrafiltration and by applying an external electric field. So, it is known as the electro ultrafiltration or electric field enhanced ultrafiltration or electric field assisted ultrafiltration. Now, in presence of electric field, what you can do, basically the problem that will arise is the decline of permeate flux. That means, during the filtration all the charged colloids will be depositing over the membrane surface. Okay. By doing that, it will increase the resistance against the solvent flux, so productivity will decrease. We do not want to do that, we would like to increase the productivity. So, what we should do, we apply an external electric field, such that its polarity will be opposite compared to the polarity of the charged sphere or the charged colloids. How will you know what is the polarity of the charged colloids? If you know the point of no charge, that is known as the isoelectric pH. If you know the isoelectric point of all the various proteins or colloids, by simply you can change the solution pH. Okay. If you set a solution pH, suppose we are talking about a protein molecule, let us say bovine serum albumin, which is having an isoelectric pH around 4.7. Okay. All the proteins or most of the proteins, their isoelectric points are known. Okay. Now, if you know the isoelectric point, you can set your operating pH, because you can use some drops of hydrochloric acid to bring down the pH, or if you can add some drops of alkali solution and can increase the pH of the solution. Now, if you set your operating pH lower than the isoelectric point, the protein will be positively charged. If you set your isoelectric point, if you set your operating pH above the isoelectric point, the protein will be negatively charged, or the charged colloids will be negatively charged. So, therefore, you can have your colloid particles charged as per your wish by changing the operating pH. Okay. So, once you know the operating pH, you will be able to know what is the charge residing of the colloidal particle, whether it is positively charged or whether it is negatively charged. If it is positively charged, then you can set an external electric field which will be having in the, let us say, it will be depositing on the bottom plate and the top plate will be, let us say, negatively charged. Okay. Then what will happen? The proteins will be attracted by the electrostatic attraction and it will move through the electrolytic solution under the effect of external electric field. So, basically it will be a complicated phenomena and the electrophoresis comes into play, and we are going to quantify that. Okay. So, the most important thing as far as your course is concerned, the potential distribution around the charge sphere. Now, the potential on the charge sphere is also it's not very clear, because when the protein particle or the charge sphere will move along an electrolytic solution, since it is an electrolytic solution, it will be having free positive anions and free cations. So, whenever a charged protein or charged sphere is moving in an electrolytic solution, it will immediately have an envelope of counter ions. Okay. That is known as the Stern layer that we have discussed in the last class. So, when a sphere will move in an electrolytic solution, it will be having a Stern layer associated with it. So, therefore, the measurement of the surface potential will not be exactly the potential on the particle, but it will be the potential on the outside surface of the Stern layer. That means, this is a solid particle which will be having, let us say, positively charged. Let us say this positive charge it amounts to be 25 E. Okay, this positive charge is around 25 E. Now, when it moves in an electrolytic solution, in the last class that we have defined that it will carry a layer of oppositely charged ions along with it. They will be strictly they will be very close to the protein surface or charged colloids, and there will be infinite viscosity. The viscosity will be infinity. That means there will be no motion of the material that is within the Stern layer compared to the motion of the sphere. That means when the sphere moves, it moves along with the Stern layer associated with it, intact with it. So, this is known as the Stern layer. So, if the surface potential is psi 0, okay, say what is psi 0? Psi 0 is nothing but q by 4 pi epsilon times a. A is the radius of the particle, and 4 pi epsilon times. Okay. So, if you know the surface charge, let us say it is 25 E. Okay. So, you can know the surface potential from the electrostatics. Now, when a layer of counter ion will be associated with it, what will be the potential outside the surface? Some of the counter ions will neutralize the charge residing on the surface. So, therefore, this potential will be psi 1, and psi 1 will be definitely less than psi naught. Now, if you use a zeta meter to calculate the potential on this charged sphere, it will never calculate its true potential. It will calculate the potential on the, it will measure the potential on the outer surface, what is known as the zeta potential, that we have discussed in elaborately in the last class. So, therefore, this system will be very important as far as our application is concerned. Okay. So, if you write down, so if you want to have a distribution of potential around a charged sphere, okay, the first thing you have to do, the starting point is the Poisson equation. And this time this Poisson equation will be in the polar coordinate, spherical polar coordinate. And since we are assuming it is one dimensional, so it is we will be using the operator corresponding to the spherical polar coordinate only in r direction, not in theta and phi direction. So, and then we use the Boltzmann distribution to formulate the Poisson-Boltzmann equation. Now, the Poisson-Boltzmann equation in the spherical coordinate, that will become too clumsy. So, use the Debye-Hückel approximation, that means surface potential is less than 25 millivolt. Then you apply the Debye-Hückel approximation, then you will be getting an equation which will be very easy to solve. Okay. So, under utilizing these steps, I am not going into details of this step because this is already done in the flat plate. The governing equation that becomes for the spherical colloidal particles becomes 1 by r square d dr of r square d psi dx is equal to d psi dr, right, is equal to kappa square psi. This is nothing but the kappa is nothing, kappa inverse is d by length. So, this is basically approximated version of Debye-Hückel approximated version of the Poisson-Boltzmann equation in spherical coordinate. Okay. And if you define a dummy variable, psi is equal to u over r, the solution becomes very simple, and it becomes, the solution becomes psi is equal to a by r e to the power kappa r plus b by r e to the power minus kappa r. Okay. And the boundary conditions are, as r tends to infinity, psi becomes 0 at the basically at the bulk of the solution, and r is equal to a, psi is equal to psi naught. That means, we know the surface potential. So, under these two conditions, the potential distribution around the charge sphere, it becomes psi is equal to psi naught A over r exponential minus kappa r minus a. So, this gives the surface potential around a charge sphere as a function of location or radial position from the center. Now, A is the radius of the particle, r is the any radial location, and based on this point onwards, what we will do in the next class, we will calculate what will be the surface potential or zeta potential that one can get under a set of electrolytic under an electrolytic solution, and that will be entirely depending on the solution electrolytic concentration, nature and things like that. Then we do simple calculations and see how that will influence about our filtration performance. Thank you.